Hi everyone. In this tutorial, I'm going to show you some advanced techniques for fitting a blend shape rig into a 4D animation sequence. You may also watch our previous tutorial that explains the basics of blend rigs and how you can use them. In this tutorial, we're going to go in depth into what parameters and what other tools can be used to make our rig fitting more controllable and accurate. If you're an advanced user who wants to increase the quality of the rig fitting, this tutorial is for you. Alright, so let's see how we can fit our rig to the 4D sequence. I'm going to start by loading a neutral expression from my blend shape rig. My blend shape rig is stored as a set of blend shapes in the form of OBJ or ply files on the disk. So right now what I'm going to do is load a neutral expression here. Furthermore, I would also like to load a texture guide for this mesh. I can find this texture guide in the gallery of Wrap. We can click the Show Containing Folder button. In the gallery we can find the Wrap Head 2 texture and drag and drop it here. Let's apply this texture to our neutral model, and here you can see our guiding texture. The next step is to load our blend shape rig, so let's create a load BlendRig node. I'm going to plug my neutral expression into this input, and I'm going to select a set of blend shapes. In this case, I'm going to select all the blend shapes in the form of ply files. I'll select everything except for the neutral expression and click Open. Now my rig is loaded and we can use a pose BlendRig node to check if the rig logic was loaded correctly. We can go to the Visual Editor tab and click Controls from Reference BlendRig. Here we can see all our rig sliders and we can check that they work as expected. Please note that controls like jaw left and jaw right can be triggered separately. To combine them into a single jaw sideways control, what we can do is go over to the editor and load our rig config file that I explained in the previous tutorial. Let's just load this rig config file and click Controls from Reference BlendRig again. Now if we go to the jaw expression, we can see a single control called jaw sideways that combines two controls into one. As you may remember from the previous tutorial, the rig config file is a simple JSON file that basically states which suffixes should be combined into which names. Alright, with that done, it's time to load our 4D animation sequence that is going to be our target for fitting. I'm going to create a load vertices node and plug my neutral expression here. Let's rename this node to sequence. In load vertices, I'm going to go to the sequence folder and select my ply sequence. So the reason why we use ply files is because ply files only store vertex positions and they don't store the topology and texture coordinates for every frame. So that's why they're much faster to load and take much less space on the drive. So let's load the sequence. Now if I scroll on the timeline, you can see the playback of my animation sequence. Alright, let's see if we can fit this sequence with our blend shape rig. As you may remember from our previous tutorial, we can use a FitBlendRig node. We need to plug our BlendRig into the first input and our target geometry into the second input. Now we can go here and click Compute, and that will start our rig fitting. Then we can use a BlendRig to Geom node to convert this rig into geometry. Here you can see how our rig solved this expression. So this is what we covered in the previous tutorial, but now let's see some actual problems that may have happened with the rig fitting. This FitBlendRig node for now solves for the vertices of the entire face. But this isn't something we want all the time. For example, it doesn't make a lot of sense to fit the inner mouth socket or the eye socket of our mesh. It also doesn't make too much sense to solve the back of the head as well. So basically, we can exclude these regions from solving, and we can do that by providing a vertex mask of the included regions. Before creating this vertex mask, let me load a jaw open expression. I'm going to create a load vertices node. I'm going to call it jaw open. And I'm going to select the jaw open expression from my list of blend shapes. Alright, this is our expression. Now let's create a vertex mask node and plug it into the jaw open expression. Let's call this mask a fitting mask. If we go to the Visual Editor tab, let me set up my brush so that I have the symmetry mode as topological. Let me click geodesic distance and increase the intensity to 100. And now I'll start to paint the mask for the region that I'm interested in, specifically the front part of the face. I would also like to cover the ears, and I can also use a little bit of the neck geometry. Now we can exclude the mouth socket and the eye sockets from this selection. We can go here and click Import from Polygroups. Then we can select the eye socket bottom and eye socket top, as well as mouth socket bottom and mouth socket top, and click Subtract. That will remove these polygroups from our selection. What we can also do is slightly remove the inner part of the lips from fitting, which is also a good idea and is recommended to do. Let's smooth the transition between the selected and non-selected parts by holding the Shift key. With this done, we can plug this mask into the FitBlendRig node. Again, we can click Compute, and that will produce our result. Let me create a transform node and translate my sequence to the left so that we can see both meshes at the same time and we can compare them. So if we solve this frame in the FitBlendRig node, you can see that it solves nicely, except for the fact that the lips are not completely closed here, while at the same time they're closed in the original sequence. It's not a desirable effect because, as humans, we naturally focus on the lips and are highly skilled at lip reading. Whenever we see that the lips are not completely closed for phonemes like b, p, m, that naturally should be done with closed lips, we feel that something's wrong. So it's super important that the lips are closed whenever they're closed on the original sequence. We can force and propagate this closeness by using spline selections. So let's go ahead and create a Select Points with Splines node. I'm going to go over here and select the spline that corresponds to the wet line of my lower lip. I'm going to click over here and start adding points on my spline. Now that I've done it, let's add a few more points to make sure that the spline is located accurately on the lip contour. So this is our spline, and I'm going to call this spline lower lip spline. Then let me create another Select Points with Splines node. This time I'm going to do the same just for the upper lip. Please make sure that your lower lip and the upper lip start and end at the same vertex. Now let's add a few more points to make sure that the spline is accurately located on the contour of the lips. Okay, with this done, let's rename this node to upper lip spline. Now let's create a StickContour node. There we go. As the first input, I'm going to plug in my jaw open expression, which is my reference shape. As the second input, I'm going to plug in my animation sequence. Then I need to plug my lower lip spline and upper lip spline. The StickContour node is quite a powerful tool that allows you to control the stickiness of the lips. For example, if we go to frame 135, we can see that the original sequence has the lips open. By default, the StickContour node closes the lips, and you can control the value of this closeness. But this is not what we're going to use. Another mode of the StickContour node is stick by distance. In this case, as I am increasing the distance, it basically creates a zip lip effect. I can change the parameters, and this is how I can create a sticky lips effect. If you go to the Visual Editor tab, you can see the exact contour that is being used to produce the sticky lips effect. By default, it works as points on triangles, but it's much better to use another mode that is called Offset Trace. This mode offsets the spline to some distance inside the lips. Then it back projects the green contours toward each order to find corresponding contours on the surface of the lips. You can see these contours marked with red. The back projection method allows the contours to slide along the surface depending on the current lip expression. Now if we go back and check the sticky lip effect, you can see that it works pretty well. But the mode that we're going to use in this case is called Stick by Reference. With Stick by Reference, the node basically watches the splines on the reference mesh and checks that the splines are closed. Then it propagates this closeness to the second mesh. So it basically copies the closeness of the splines from one mesh to another. To make it work, we need to plug in our reference mesh, which is going to be treated as the source of this closeness. To make it work properly, we can create a Fix Intersections node. I highly recommend doing that before this operation. We can go to some frame, like this one. You can see that the Fix Intersections node basically fixes the intersections between the lips. It makes the detection of the thickness much easier and much more precise. Instead of solving the intersections for the entire mesh, we can explicitly specify the vertex mask where this intersection fixing is going to happen. So let's create a vertex mask and call it intersection mask. I'm going to plug in my jaw open expression. Let me set the symmetry to topological, click use geodesic distance, and set the intensity to 100. Then let me select just the inner contour of the lips where intersections may take place. Let's also select a little bit inside of the lips. We're only going to fix intersections inside this mask. Now, let me plug this mask into the Fix Intersections node. The Fix Intersections node in this case will work much faster because it has much fewer polygons to work with. The next step is to plug the result of the node as a reference to the FitBlendRig node. In this case, we don't really need the output mesh, but we need the detection of the contours for the upper and lower lips. So we are only interested in these two outputs. We can use a points-to-point pairs node and combine those contours into point pairs. The next step is to plug this points-to-point pairs node into our FitBlendRig node. To demonstrate the effect of this change, let me copy and paste using Ctrl-Shift-V our FitBlendRig node over here. But this time I'm not going to plug in my contours. And let me also change the color of these nodes to gray. If I go to this node, I can click Compute, and that will give my result. Let's go back to that problematic frame 509 and compute it. Let's see how it was being computed before using the contours. As you can see, this is the result before, and this is the result after. You can see that the new version basically closes the lips the same way as they were closed on the original animation sequence. Let's go and see another case, for example, frame 1144. Here we can see a closed smile expression. Let's go to the old version and click Compute. And we can see that the old version failed to completely close the lips. Let's go to the newer version and click Compute again. In this version, you can see that the lips are properly closed, thanks to the splines. We can do the same trick for the eyes as well. In this case, for the sake of time, let me just copy and paste my contour selections for the upper and the lower eyelids. Here you can see the lower eyelid and the upper eyelid selection. Then let's use a points to point pairs node and combine them into a set of point pairs. You can see that there's an error over here that doesn't allow us to match those points because they have different names. In this case, what you can do is to switch the match by mode into alphabetical order, and now they are matched correctly. Now we can plug them into our FitBlendRig node. Now let's do the same for the second eye. I'm going to copy and paste the selection here. Let me plug in the original geometry. And let me also create a points to point pairs node. And plug the selection over here. Now if we go to some interesting frame, for example like 1265, you can see that the eyes are almost closed over here. If we see the previous solve, you can see that there's a pretty big gap between the eyelids. Now if we solve it with the new version, it's going to improve this closeness and make it better compared to the original result. One more thing that can be improved is to resolve the ambiguities in the solving process. For example, if we go to the Pose BlendRig node and look at the logic of controls, you'll see that we have a jaw open expression and a jaw open extreme expression that are both used for opening the jaw. Basically, we want to instruct the solver to use the jaw open extreme expression only when it's necessary, whenever there are no other options. We can do this by adjusting the FitBlendRig node parameters. Here, in the list of control names under control name weights, we can add a line. Jaw open extreme 1. The 1 means the weight that's going to be applied to make using this control harder for the optimizer. We can use values like 5 or 10 or more if we need to prevent this control from being triggered unless it's absolutely necessary. This way, you can also restrict other controls from being triggered. It would be worth adding here all the tweakers. For example, we have multiple ways of closing the lips. We can close the lips using the lip together control, or we can close the lips with our lip stick tweakers. By giving the lip stick tweakers a bigger weight, we enforce the solver to try to solve it with hero expressions, and only if it's impossible will it use the other expressions. So in this case, let me just copy and paste this list of expressions here with their weights, and that will make our solve less ambiguous. Let's click Compute again. Alright, the last bit on how we can improve the rig fitting is related to the gaze direction. So if we go to, let's say, frame 243, we can see this kind of eyelid shape. By looking at this eyelid shape, it's quite hard to tell if the actor is actually looking down or if it's basically a combination of a blink and an eye squint. In the same way, for the solver, it's very hard to decide if it's a look down expression or an eye squint or eye blink expression without knowing the gaze direction. So let me show you how you can utilize the direction of the eyeballs to help the FitBlendRig solver. For now, let me click Ctrl D to disable the Fix Intersections node since it's computationally intensive. Aside from our 4D sequence captured in the HMC, we also have the gaze tracking. Let me load this gaze tracking over here. I'm going to go into our sample folder and load my eyeball geometry. This eyeball geometry is basically a template eyeball that is located in the middle of the world coordinate space. Then, I can also add a texture for my eyeball and apply it here. Then I can load the rotations of my eyeball as a set of transforms by using a load transform node. I'm going to call this node left eye rotations, and I'm going to select the left eye transform sequence. Now if I scroll through the timeline, you can see that the eyeball changes its rotation. Currently, the eyeball is located at the origin. I can bring this eyeball back to the eyelids by using a predefined transform. I'm going to use another load transform node. Here, I'm going to load my transform that brings my eyeball from the origin to the left eye socket. Now I can scroll the sequence, and you can see the eye animation playing in sync with my 4D animation. We can do the same for the right eye. Let me start with copying these nodes. I'm going to rename it to right eye rotations, change the folder name to right eye transform, and also change this file name to the corresponding one for the right eye. Now if I play back the sequence, you can see that the gaze works correctly. What we want to do is convert these gaze rotations into control values for the eyes, in the range of -1 to 1 for the eyes going from left to right and from down to upwards. Then we need to provide these computed transforms to our FitBlendRig node so that the node, instead of trying to compute these values, will just use these values as fixed ones. We need to start by computing the relative transformation of the eyeball rotation compared to its rest pose. One thing you can do is scroll through a sequence and find a pose where the eyes actually look neutral. Something like that. The sequence I'm using in this tutorial and the ones that come with the gallery is quite short and doesn't contain a lot of eye rotations. So let me just load a predefined transform for the rest pose for the eyes from another sequence. I'm going to create another load transform node. I'm going to call it left eye neutral rotation. Here, let me load the neutral rotation for the left eye. You can see that this is the rest pose for the left eye, and this is the current rotation. What we need to do is calculate the difference, the relative transform from the rest position to the target position. To do this, we can use a bake transform node to bake the result of the rest transformation, and then we can use a find transform node to find the transformation from this starting pose to our target position. This node will produce a transformation relative to the rest pose. If you right-click and go to Node Information, you can see the actual rotation values that we've computed with our node. Let's plug the result into the transformation node. And let's repeat the same actions for the right eye. I'm going to copy and paste this block over here. I'm going to change the name of this node to right eye neutral rotation. And let me also plug my find transform node to the loaded transform from the neutral to the eye socket. So right now we have the same animation playback, but now we can plug these relative rotations into our FitBlendRig node. On the first input, I'm going to plug my left eye rotations, and on the second input, I'm going to plug my right eye rotations. But those are just relative rotations. To convert them into meaningful control values, like -1 to 1, we need to normalize them. So we need to set the minimal horizontal rotation for the left eye going inward and the maximal rotation when going outward. If you go to the FitBlendRig node and switch to the Fit Eye Params tab, you can click the Fit Eye using Transform mode, which will use these eye rotations. Here you can specify all the ranges. These values are set up by default, but may not be very accurate. What you really need to do is look through a sequence and find some key expressions where the eyes look absolutely left and absolutely right. For this, it's better to use some range of motion sequence. When you find this kind of expression with the eyes looking left and right, you can go to this node, click Node Information, remember the amount of rotation of your eyeballs vertically and horizontally, and then go over to the parameters and copy and paste this rotation. In my case, I've already done that, so let me just copy and paste the values of rotations for each eyeball into these fields. Please note that you only need to do it once per your character. Alright, now with this done, we can enable our Fix Intersections node again. We can switch our FitBlendRig node into Auto Compute mode, and that will compute our rig fitting. We can compare it to our previous fitting results without using the gaze direction data. You can see that it's similar in this case. If you go to an interesting frame, like 243, you can see here that the eyes were looking straight, but now the rig fitting, instead of just computing these values, will take these values from our rig transform. If you compute the previous result, you can see that the results are quite different. Let's see another frame. And again, you can see the results between the computations are quite different in this case. Alright, so let's delete this node for now. And let's also arrange our graph by grouping this part of the nodes into a group called lips. Let's add a color for this group. Also, let's group this part of nose as eyes. And let's assign a different color for this group as well. So this is how we can fit our rig. Now we can save the result of this rig fitting using a Save BlendRig Controls node. Here we need to specify the path to our export folder. In this case, it's going to be Control Export. And I'm going to name the file as frame##.json. Now, if we click Compute Frame Range and specify the number of processes, for example to 8, and start computation, that will batch process the fitting of the rig for the entire sequence. I've already done that, and we can look at the result of this fitting. This is how it looks like. You can see it looks pretty nice, even though the shape is not exactly the same. But then if we go to some interesting frames, for example, frame number 760, and if we scroll through the neighboring frames, you can see that there's a jump on the lower lip on our solve. There's no such jump on our original sequence. The solver of the rig produces a jump, most likely because of the ambiguities in how this shape can be solved. We can also look at another frame, frame 710. Again, if we scroll back and forth, you can see that there's a jump of the cheek during this expression. The way we can solve this problem is basically to run the solving as a second pass, but this time we're going to use the controls from the previous pass as an initialization, and we're going to use a smooth version of these controls. Let's see how we can do that. We can basically copy this project under a different name. I'm going to call it Advanced BlendRig Fitting Second Pass. Now I'm going to use a smooth BlendRig controls node. Let me plug my BlendRig as an input. Here I need to specify my sequence of BlendRig controls computed on the first pass. Let me load it. Here you can see some parameters that define the smoothing value of my control sequence. I can increase the neighbor to 2 for even smoother results. Now what we can do is pass these controls as the first input of our FitBlendRig node. Then inside the FitBlendRig node, we can unselect Make Prefit and make sure that Use Current Control as Init is selected. Then we can go over here and provide the initial control weight. This is the weight that will hold our solution close to the smooth solution. In this case, I'm going to set a weight of 30. With this done, we can go through different frames, and that will compute the rig fitting for every frame by using the smooth result as initialization. Now we can use a Save BlendRig controls again. Now we can save it to a folder called Control Export Second Pass. Click Compute Frame Range and compute all the frames. As a result of this operation, we're going to have a sequence like this one. Now if we go to the same problematic frame, like 760, and scroll through the sequence, you can see that there's no jump on the solve here. Also, if we go to another problematic frame, 710, and again scroll through the sequence, you can see that there's also no jump on the cheek. Alright, so that's all for this tutorial. I hope you found it useful, and see you in the next video.